Welcome. This question says, consider the interference of two sound waves that are in phase. The distance r1 is 2.2 meters, the distance r2 is 2.8 meters, the wavelength of sound is 0.4 meters. It says, show that the phase difference at point P is 3 pi radians. So here's the visualization. We have a source of sound 1, source of sound 2. When it says they're in phase, it means that they're both pushing when they push and they're both pulling when they pull. So the pattern, they create compressions at the same time, they create rarefactions at the same time. So I don't need to take into account a phase difference between these two in this question. So these waves travel through space at a certain speed, same speed for each of them, but the distances that they travel are different. And so what happens is, when I get here, one of them might be doing a compression while the other one's not doing a compression, might be doing a rarefaction. And so we'd like to be able to express what's going on here in terms of that interference. So if I imagine at point P, I have one wave coming in, and let's draw it. So I have one wave coming in looking something like that. I'm drawing the pressure versus position. And then for the other wave, I have something, sorry about that, for the other wave I have something that looks like that. So I'm actually kind of drawn them. So you look here and you say, oh, that one's at that point in its cycle and that one's at that point in its cycle, and so they're going to, add. So it wants me to find the phase difference, and the phase difference is the difference in the where through the cycle each wave is at this point P. And the way I can get there is I can say, well, look, there's a crest and there's a crest. So they're out by this fraction of a wavelength. If I finish off this wave, then they're out by, if that's lambda, and that's how much they're out by. They're out by that part of a complete wave. I need somehow to express that, and I could express this path difference effect because it is caused by a path difference. I could express this path difference effect using meters. So I would say my path difference effect equals my length 1 minus length 2, or in this case R1 minus R2, which in this case is 2.8 minus 2.2, which equals 0.6 meters. I could express and that's in terms of meters if you like. I can turn my path difference, I can express it in terms of wavelengths, and that's going to equal my path difference in meters over the length of a wavelength, which would be 2.8 minus 2.2 over, and it says that the wavelength is 0.4. So that would be 1.5 lambdas. Or I could express my path difference in terms of an angle. Now here, I'm using this idea that a wave can be thought of as a series of revolvements in phase space, if you like. So one wavelength would be 1 times round, half a wavelength would be half a times round, 3/4 of a wavelength would be 3/4 of the way round. And I could do this in degrees. Let's just go through the whole thing. I could do this in degrees. So that would be, well, 1/2 wavelengths is 1.5 times around the circle, which is 1.5 times 360, which is 360 plus 180 is 460, 540. If I did my math right. And then the final way of expressing this is the phase angle in radians. And that is, well, each time round, each circle is 2 pi radians, so it would be 1.5 times 2 pi, which equals, what would that be, 3 pi radians. And that is in fact what I was asked to show. So, you know, I recognize that this is no phase difference at the source, so I don't need to worry about that. We'll talk about that later. I'm only interested in a path difference effect in this situation. So my path difference I could express in meters and say just take one from the other. I could express my path difference in terms of wavelengths of the wave, and just divide the path difference by the wavelength. I could then express my path difference in terms of degrees, because each wavelength is worth 1 revolution, which is 360 degrees. And then finally, more commonly, I could express my path difference in terms of radians. So because each wavelength is like going around the circle once, which is 2 pi radians. There is an equation you can learn, and the equation says that the phase difference is equal to basically R1 minus R2, and you don't care which one's biggest, so you put the you basically don't worry about the sign, over the wavelength times 2 pi. And it's there, and you know, it's in the book, and it's in my notes when I teach, but I don't need it because I can just visualize it and get this. So I think here's an example of do you learn an equation just to learn an equation, which is supposed to represent a visualization, or do you just worry about the visualization? And to my mind, I worry about the visualization. Whichever way you do it, there we have it. And so the answer is 3 pi radians.